Hi everyone, this is the Algebra 2 unit or Algebra 2 semester B unit 10 course activity. So we're gonna go ahead and get started. Moving on to, I think there's a first question on slide 3. So remember when we went over standard deviations within a normal curve? We're going to go ahead and take a look. So this should be a little bit of a review for you already. But here we have the bell-shaped curve. Oops. Let me go ahead. So here's your bell-shaped curve, and it comes, and we try to test out depending on the sizing of the standard deviations. So in the center here, you would have your mean value, and the standard deviation is whatever value is your standard deviation is how much it goes farther apart, and it's stuck between two numbers. The mean always stays in the middle. So technically, if this is within one standard deviation, you're gonna pretty much cover this whole area in this under the bell-shaped curve. Now the question is, what is the percent that relates to this when it's between one standard deviation? So remember, under the whole curve, we have, this is supposed to be technically under 100%. So when we look at our options here, within one standard deviation, does this colored in green look like it's 95% filled, 99.7% filled, or 68% filled? And then you go ahead and select that one for your first standard deviation. Within two standard deviation, it goes more farther apart. So then now I'm talking about, now what I'm going to go ahead and color in blue is not only going to cover the green area, it's going to include the green area and all of this. So again, what's your best estimate on what's the percent that is being covered in here? Again, under, if this whole curve is technically 100%. So then you go ahead and select that one. Within three standard deviations, we're going to go ahead and go farther apart. So this one thing this curve doesn't do is that it doesn't actually touch the axis down below. It curves off, because again, in statistics, as much as our goal is to try to get 100% of it, most of the time, if we're even getting a 99.7 or 95% is still high enough to get a good idea of what we're taking, what statistics we're taking here. So if we go ahead and do this in pink, what's the percent here that we have within three standard deviations? So it's, do you see how, again, they kind of overlap each other? So the third standard deviation is all of this in pink, and you'll just go ahead and relate that back to the percents down below. Again, you have three options: 68%, the 99.7 and 95. So one standard deviation, and then it continues to increase as we go. So go ahead and select those options there. We're going to go ahead and move on to the first task. We are going to look at two different concepts that we're really introducing to the tutorials. And the first one is about re-randomization. So we're going to select a sample. And the sample, we are going to say, take a group of people. So like this one right here on slide 7, and we're going to break up the group into two separate groups with an even amount of people. Now, if we do that, right, this one's going to receive the treatment. This one's going to receive no treatment under the control group. But that's the first randomization. So what they could have done is that they first selected these people, and then they selected these people for the control group. So they separated. Or we can do it another way. Maybe I want this group to be separated like this. Oops. That's 1, 2, 3, 4. And then we can separate the group like this: 1, 2, 3, 4, 5. So there are different ways to kind of split the group in half. And every single time we separate them, it's that's gonna be called our first randomization. So going into task number 1 on slide 9 is that you have these peppers, these green bell peppers, and you weighed each green bell pepper, and you have 10 of them. So you're technically, think of group A versus group B as in 2 baskets. We're gonna, in group A or basket A, we're gonna put 5 bell peppers in the basket, and we're gonna put another 5. The thing is, it's like you technically have it in one bucket and you have them all mixed together and you separate them randomly. So not only do you do that one time, you get this first randomization. You take all the chili peppers or bell peppers, put them back in the basket, shake them up again, and separate them another time. And then you repeat the process to do a third randomization. So for this first part A, for the first task, is we're trying to find the mean. Or in other words, you're trying to find the average weight of each randomization. So this one is coming from the first table, this is coming in from the second table, and we're gonna go ahead and do the third table. So I'm gonna go ahead and work on the first table with you, and then you're gonna repeat the same process for table 2 and 3. So, and recall that in order to find the average weight or the mean weight, you're gonna technically so this is gonna be for group A. So again, I'm doing the first table here. I'm gonna take all of these values and add them up together and then divide them by how many I added. So give me one quick second here. Okay, so I went ahead and went to set up finding the mean for each group. So for group A, again, we take all these values and we add them up and we divide it by how many we added. So there's a total of 5 numbers. So you're going to be dividing by 5. And again, this is the same steps that you're going to repeat for the second table and the third table. So when going back over here, so for group A, if I add them all up, I get a value of 62.5. And I still haven't divided by 5 yet, so I'm gonna have that there. And once I do divide by 5, I get the final average weight of the basket here as 12.5. Now we go ahead and move on to basket or group B. I call them baskets, but groups, same idea. I'm gonna go ahead and add up all those values again and then divide by 5. We're gonna go ahead and get 57.3. And then we're gonna divide it by 5. And the average weight here is 11.46. Now, those are the 2 values that you're gonna go ahead and enter down below here. So I know I have it blocked, but under X bar of A, it's gonna be 12.5, X bar of B is 11.46. Now for the third box, again, on that first line, that's asking you to do subtract the mean weights of A minus B. So that's why I have this little setup down here below. So for A, we got the value of 12.5. So right here, we're gonna put 12.5. And then for B, we have 11.46. And again, you're gonna set it up. It's always gonna be A minus B. Now also kind of think about it, because this is gonna help you out for the rest of the questions after these, is that which basket is technically heavier? So this has an average weight of 12.5 and this has an average of 11.46. This kind of tells me that basket A is a lot more bigger or heavier in a sense, right? Because it's weight. So when we do subtract these two, we get 1.04, which is going to be the third value that you're going to enter in that third box there. And again, you'll just go ahead and do the same thing, same setup for second randomization for the second table and then for the third. So going back to that idea that basket A is heavier by 1.04, I think it's in ounces, yeah. So basket A is heavier. So again, when you make sure, I like this setup only because I get to compare them, like visually see the comparison. But let's go ahead and take a look at part B. So part B is, let me go ahead and clean this up. It says, what do large differences mean for each group indicated? So that's why I kind of have this concept here still, because if we have a difference, right, I get a value here. In this case, we have that A is actually larger by 1.04 ounces here. So it says a large difference does not indicate any significant meaning. There is some type of meaning there, right? There is not enough information to analyze the difference. We're able to take the difference. So do you see, we kind of eliminated these two already. The peppers with the different weights aren't properly distributed between the two groups. Sounds like it, right? Because again, group basket A or group A weighs a little bit more, weighs more than group B. So this one's kind of the answer we're looking for. But to double check, it says the peppers with different weights are properly distributed between the two groups. When we're trying to properly distribute, is that we're trying to make it balanced. So we want to make it, so here we know it's unbalanced because again, group A weighs more. So this is our final selection here. Now, this is when it's unbalanced. What value do you think if we have it balanced? So this is a completely different example, but if we want it to be properly distributed, meaning balanced, say this has a weight of 5, to get it balanced, wouldn't B also need to be 5? And if we subtract the difference, 5 minus 5, we get the value of 0. So 0 kind of indicates that we have a balanced distribution. But let's go ahead and take a look into part C. So it says the mean difference. So after subtracting from group A and B, the mean, the difference of 0 indicates that the peppers are or are not well distributed. So remember, well distributed would be, in other words, are they balanced? So if we get 0, can we say that the two baskets are balanced or not, or are not balanced? Go ahead and select your answer for part C. So let's go ahead and move on to the next task. So moving on to task number 2 here, applying the level of significance. So what we're gonna, applying the level of significance is that they're gonna tell us what level of significance we're looking for. If it's below it, if we're below it, we're good. If we're actually outside of that 5% significance, or actually, yeah, the level down right here, consider the significance level to be set at 5%. So the results less than 5% can be considered statistically significant. Now, if it is more than, we can say that it's not statistically significant. So we're going to take a look at this one right here. So it says, researchers want to find a way to increase the growth rate of corn so it can be harvested more often. To test the effectiveness of the new type of spray fertilizer, plants grown from 200 corn seeds were divided equally into 2 groups. So they're also applying the re-randomization concept with the bell peppers that we did in task 1. So it says that the treatment groups were frequently sprayed with the new type of fertilizer. The growth of the in centimeters of each corn plant was noted before and after the treatment. So the results show that the mean change in the growth. So that idea, what you did in the table, you found the average rate, you found the average for group A, then you found the average for group B. Then what we did was we did A minus B of those 2 groups, and then we have that value. So here, it says the results show that the mean change of the growth rate by the treatment group of 8 points or more than the control group. So treatment group, right? So it's this idea here, treatment minus control group, when it was equal to 8 points or more, right? And down down this whole list is your point, is the points. So when it was 8 or more, so the results show that the mean change in the growth rate by the treatment group is 8 points or more more than that of the control group. To test whether the results could be explained by random chance, researchers created a table to summarize the results of 1,000 re-randomizations. So that concept of you, in the first task, you did it only 3 times. Here are the results if they did it 1,000 times, repeating that whole same system and collecting those results. So with that happening, right, they says the difference of the means rounds to nearest 2 points. Consider the significance level to be set at 5%. So we're looking for when it's 8 points or more. So with this right here, so going back to this, so we're looking for 8 or more point difference. So we take a look in this area, we're gonna technically look for 8 points or more. Here, we're not looking in the negative because again, we're looking for when the treatment group is up 8 more points or more versus that control group. So starting right here, we have our value of 8. And again, we're going to consider 8 or more. So that's including our 10 and 12. Everything above this that's not highlighted is technically 8 or less. Now, the case for this this happened 26 times for when it was 8 or more, 10 or 8, and then when they had a difference of 10, that happened 8 times, and then 12, that happened 2 times. So keep in mind down here for part A, what we're going to go ahead and look at is the significance level of 5% of the probability results in. So in order to find that percent, right, of when it was 8 points or more, we're going to take these 3 values right here. So we're going to add them up, 26 plus, oops. So we're going to do 26 plus 8 plus 2. And we're going to divide it. Remember, this is the frequency out of 1,000 re-randomization. So you're going to divide this whole thing by 1,000. So then when we add this up, right, 8 plus 2 is 10, 10 plus 26, you can add up to 36. Don't forget, you're still dividing by 1,000. Now, when you divide this, you get 0.036. But this is in decimal form. I want this in percentage form. So to convert this to percent, you just take your decimal, drag it over twice. That's the new point. So that looks at 3.6%. So now think about it. Is this result statistically significant? Right? So we go back here to find our percent. There's our 3.6, which is the same as greater than or less than the significance level. So remember, the significance level is at 5%. So you're going to go ahead and select this 3.6, the same as greater than or less than 5%. And remember, the idea is that it is, if it's less than 5%, it is considered statistically significant. So then here, after your option, is it considered significant, not, or inclusive? Well, there's only technically 2 options there, right? It's either statistically significant or not, because the idea is when it's less than, right? We're going to choose, yeah, it is. When it is more than 5%, it's considered not. So go ahead and enter your answers there for part A. Now, depending on your idea here for statistically significant or not, you should have already agreed that 3.6 is less than 5%. So it does work. It is statistically significant because it is less than the 5%. So when we're reading these results, right, That because it's considered statistically significant, going back to the context of the problem, it means that that new spray fertilizer did work for the 200 corn seeds. So here we can say the results is statistically significant, which implies the spraying the corn plants with a new type of fertilizer does increase growth rate. The results is not statistically significant, which implies that the spraying of the corn plants with the new type of fertilizer does increase the growth rates. The results is not statistically significant, which implies, what happened here? Which implies that the results could be due to random chance. The results is statistically significant, which implies that the spraying of the corn plants with the new type of fertilizer does not increase. Well, the whole idea about the concept is that, is it going to increase to harvest more corn? So we know it is going to be statistically significant. So we can automatically eliminate this choice because it's not. This one is also not. So the question is it this one or this one here, right? Because these both are stating that it is statistically significant. So because it does the fertilizer help increase growth or does not increase growth? So remember, it does work. So we're going to select, you'll select that one down below. Moving on to question 2, we're going to do the very same concept, but now we're going to go ahead and take a look at a study about, I think it's like a study of 300 college students, right? So I'm summarizing a little bit here from the word problem here. But 300 college students are asked to wear a watch to see if that helps them manage their time instead of using a phone. Now, keep in mind, think about it to yourself. Does a watch really help you manage your time? I think to me, watches are more like of an accessory. It doesn't, I don't think I look at my watch that much when I'm wearing one to look at the time. But they want to know if they can wear the watch instead of using their phone to keep track of their time. So the idea is, I think they they keep score by seeing if they attend class on time or not. I think managing time has to do more with that. So we're going to kind of take a look into this study of it. So it says that this is kind of like the most important part. Again, think about it, the significance level is going to be set at 5%. So if the results are lower than 5%, then it can be considered statistically significant. So we're looking for that percent, and either it's going to be less than 5 or greater than 5. So less than 5 means it's statistically significant. Greater than means not statistically significant. So going back here, so it says the results of the experiment showed that the mean score of the treatment group was exactly 15 points less. So that idea where they're saying less is that I'm looking for 15 points below. So that means that my control group was higher, meaning I have a negative value for the difference. So 15 points less than the mean score of the control group. To test whether the results can be explained by random chance, the researchers created the following table, which summarizes the 1,000 re-randomizations. So again, very similar to the concept of task 1, but they went ahead and did it for you. Under frequency, that just tells us how many times it has happened. So for this one right here, right, we're looking for negative 15 points or less than that. So if we're looking for negative 15, we're going to look up here at the top part of our chart, and we can see that we have negative 15. Anything less than that, negative 20 is less than that, and so is negative 25. So you can see we're going to repeat the same steps here. We're going to add up our 3 values here of how many times each of those points happen. So we'll be adding 10 plus 18 plus 50. And we're going to divide it by 1,000 be for the 1,000 re-randomizations. So if we add this, 10 and 50 is 60. 60 plus 18 is 78. Over 1,000, we get 0.078. Now down below, it's asking us for the percent. So you move that decimal over 2 points to the right or 2 to the right. So we go 1, 2, it's between 7 and 8. So our percent here is 7.8%. So now that we found our percent is, now remember it says 7.8%, which is what? Then our significance level. Remember our significance level is set at 5%. So 7.8 is less than, the same as, or greater than 5. And remember, it is considered statistically significant if it is lower than 5%. So is it less? It's going to be less than statistically, or it's going to be considered statistically significant. If it is more, it is not. So go ahead and select your options there. For part B, we are going to see that 7.8 is larger. So it does imply that we have a significance level that is, or considered, it's not statistically significant. So right here, the result is statistically insignificant. That is automatically no. The result is not, we like that. The result is statistically significant. We know it's not that. And the result is not statistically significant. So now we have to look at the reason for it. So it says, which implies that wearing a watch does not help manage their time better, or it says, which implies the results could be due to random chance. So I didn't point it out. I know I did talk about the concept of how we're testing out if wearing a watch helps you out with time. We're kind of it kind of hints off that this would be the answer. But remember, doing this re-randomization is all on chance. So like if we go back on here, it says to test the study's results, researchers randomized 300 college students. The treatment group was asked to watch every day and watch every day. The control group were asked to avoid wearing watches for 50 days. The results of the experiment showed by the mean score. Where is the wording? Give me a second here. So right here, I was like taking a moment to read that, but to test whether the results could be explained by random chance. So this idea, so because this is considered not statistically significant, right? Those options that we're left with down below, we know it was between this one, the second option, or the first or the last one. The question is, we don't really know. We would probably have to do more investigation or more testing it out, maybe a different way of looking into it, because again, how does time management show depending on if you arrive early or not? So this is which implies the results could not be, or the results could be due to random chance. And we're gonna go ahead and select this option down below, and we can go ahead and take a look at the next task over. So we are going to go ahead and take a look at the Alberoni, which is the red box or the blue pasta box. So there is a science behind this. We use statistics in almost every way of life. If you think about it, how we can take statistics depending on a new trend, or if there's a show that I do like, where there's a whole science where they remodel, I think it's restaurants. Is it restaurants? One of those, I can't think of the name. But the idea is that there's a whole science to everything that we buy in terms of products as well. So you can take it, for example, McDonald's. Why is it such a successful fast food place? Or in other words, why do we drive anywhere and every 10 minutes we pass by McDonald's? It's a big fast food chain, sorry. Now, the concept that I've read before is that there is a reason why McDonald's was considered or in the colors of yellow and red. So our eyes are attracted to certain colors. There's like another statistics where a police officer is more likely to pull over a red car because the eyes are attracted to red cards or incense the color red. So would there be a difference if we go to the store and buy pasta, right? It's the same brand, Alberoni, macaroni and cheese, Alberoni, macaroni and cheese. The only difference is it a red box or a blue box. Is there some statistics behind it where people prefer the red or the blue? So that we're going to go ahead and jump into that here in task number 3. So the first thing they're asking us is that they took a sample. So it says, as a member of the marketing team for the pasta manufacturers, you want to find out whether there's a difference in the mean number of people who would buy the new macaroni product Alberoni if it had a red box and if it had a blue box. So is there some type of difference there? So it says in each session, you bring 30 people to try Alberoni and have them respond to whether they would buy this product. So people went out to go ahead and take surveys with people, and we're going to click on this data sheet. So if you don't have Microsoft or Excel, because it is an Excel spreadsheet, we're going to go over here. This is the data that they collected. So if I scroll up here, give it a moment. So this is the results for the package in red. These are the results for the package in blue. So going back to this right here. So again, so these are the results of the market testers. So the first, kind of going back over here to part A, it says find the mean value. So we're finding the average for the purchases of the red box and then the blue box. So with the Excel spreadsheet, it is very time consuming. If we had to add up all these values, there is 45 of them. So with Excel, there's a beautiful option where we can go ahead and select the average already, and it gave it to us here. So we'll go ahead and put that on the side here. So for the red box, and again, we're rounding it to 2 decimal places, or to the nearest 100th. So this is 15.11. Now we're going to go ahead and do the same thing here. So when we go down here to select mean, I'm going to hit the equal sign and I'm going to type in average, open parentheses, and I'm going to select all these boxes here. So the count is on the left-hand side, right? But I want to know how many times they would purchase it. So we're selecting all these boxes and I should hit close parentheses and enter. And I get the mean value for the blue box to be 16.85. So for this option here, we didn't have to go ahead and do it by hand. It was just using the Excel spreadsheet. So now going back over here to part A, we already have our setup, right? 15.11 for the red box, blue box is 16.85. Now, what I didn't mention up beforehand was we went straight into the data sheet, but we're going to use this information to go ahead and use that for the very last question. But I'm going to have you work on part B on your own. So it says, what is the difference of the sample means? So these two values, what's the difference between them? Or in other words, you're going to go ahead and subtract them. So go ahead, take out a calculator, or you can go ahead and subtract by hand, but you're going to do 16.85 minus 15.11 and select your difference there. Now let's go ahead and take a look at part C. So in part C, we're going to use that equation that we had listed up above. So let's go ahead and take a moment to get that written down here. So what I did is that I took the equation that we have written, that was given to us written above. So this little symbol right here is considered the standard deviation, which is given to us right here. And then N is actually the sample size. So if we take a look at the sample size, going back to our Excel spreadsheet, which is technically going to be set up here. Now, I know the equation is set up for N1 and N2. What I did here is that I put it of R and blue, or R and B for red and blue, just to help us organize our information there, because we're going to move it into the calculator. So for the red box, if we go back to the sample size there, scroll down below, the red box had a sample size, right? Red is on the first one, 45. So we know that our n of r, or in other words, n of 1 is set up to be 45. Now, if we take a look under the blue box, they had a sample size of 60. So they set that to be n of 2, or what I'm going to do is I'm going to set this up as n of b for 60. So going back to the problem here, n1, we have 45. Again, that's just pulling information from the Excel spreadsheet. Then we're going to have 60. Now, to find the standard deviation of the sample mean difference approximately, we're going to use this equation. So we're going to set it up here first on the screen, and then we're going to go over here to the scientific calculator. And I'm going to show you how to set that one up. So here, it's the standard deviation of the red box squared. So here's my standard deviation, 3.868. So I'm going to put this in parentheses, 3.868. And we're going to put this to the 2 power all over. Now it's the sample size of the red box, which is 45. Now it's going to be plus the parentheses. We want the standard deviation of the blue box. So that's 2.933. So we have 2.933 to the 2 power. And this is going to be all over 60 for the sample size. So now let's move into the scientific calculator. So I definitely recommend the Desmos scientific calculator. So if you open up a new tab and search it on Google, Desmos scientific calculator, it should be the first link there. So I'm going to show you how to set this up and what it should look like. Right on the right hand side over here, which I'm kind of blocking out, is going to be the final answer. So once you set it up, by following me, how we're gonna set this up. Oops. What you're gonna go ahead and do is that you're gonna round it to 2 decimal places. So again, the standard deviation. So then you also have a couple of options too. So you're gonna be set up just fine for this. So if you follow along with me, the first thing we need to build is the square root. So there's on the keyboard down below, here's your square root option. Now you do have a triangle, my mistake. You have a fraction set up first. So I'm gonna hit the divide button and that's gonna set up my fraction. So the next thing is I'm gonna do the top part, my numerator, the fraction. So I'm gonna start it with parentheses. So I'm gonna, if you're following it, again, we have the square root. We hit the divide button to set up our fraction. I'm going to start with the parentheses. So down below here, you can even type it out if you like, but I'll show you through the keyboard option here. So I have open parentheses and I'm going to enter this decimal here. So it's 3.868. We're going to close up the parentheses and I'm going to set this to the 2 powers. So you can click on this A square button and there's your power of 2. Now bring over your cursor to bring it down here and we're going to enter that bottom number, which is 45. So now I'm going to move my cursor to the right. And do you see I'm at the very end of the fraction? What could be helpful is on your keyboard using the arrow. I'm going to put the plus sign. So again, I'm building this whole thing now. So then we need another fraction. So we're going to select the divide and open parentheses. And we're going to enter this value, 2.933, close up the parentheses, and we're going to square it. So then on the right-hand side, your answer should start building up. Now, because I still haven't entered a value there, you should have some type of triangle, like saying it's an error. That's because you're not filling it out just yet. But now down below, we're going to go ahead and enter 60. And that should be your final answer over here on the right-hand side. I have it blocked, but if you follow those steps, right, you are going to round your answer to 2 decimal places. So rounding it to 2 decimal places, and then we're going to go back here and select the best option there. So again, round it to 2 decimal places. Moving on to the next task, which is task number 4. So keep in mind, you are going to want to keep your information that you got. Actually, maybe I should go back. You want the mean difference, which is going to be part B from the previous task. So you want to make sure you have that value. And you also want to have the value, the one where we entered it onto the calculator. We're going to need that here for the next task. So keep in mind, in the tutorial, we covered where you were looking for confidence intervals within the 95%, within the 95%. So the idea is that you found these two sets of numbers and the mean had to be somewhere inside. As long as it was inside, we were good. Now here we're doing the opposite. Instead of finding the 95%, we're looking for the 5%. If you think about it, that both adds up to 100 if you put them together, 95 and 5. So instead of looking within, we're trying to like find the interval, but then looking for it in a sense of on the outside. So it's like we're kind of working opposite of what we were seeing. This again should be a little bit reviewing. You kind of saw that in the first in that first question that we saw, I think was on slide 3. Here's your mean value again in the middle, and within 1 standard deviation, you have it set at 68. Then within 2 standard deviations, remember, as we increase, we're including everything between those two. It's 95. Then we go to 3 standard deviations, we get to 99.7. So let's go ahead and move into task number 4 here. So when we're looking for the 95% confidence interval, we are going to use the information here. So task 4 does give you a hint off, so you can double check your answers here. It says you calculated a standard deviation of a sample mean of 0.69. So you should have gotten 0.69 when you set this one up. So right here, 0.689, rounded 0.69. Now the sample mean difference was 1.74. So now what we're gonna do is to find the 95% confidence interval. Now remember, 95% confidence interval was in 2 standard deviations. So we're gonna use our sample mean difference here. So the standard deviation sample mean difference here, 0.69. And because we're looking for the 95% confidence interval, that's within 2 standard deviations. So if this is the standard deviation, we're going to multiply it by 2. Here, we're going to multiply 2 times 0.69. So once you have that value, you're going to have the positive and the negative value there. So then our confidence interval is going to be between what 2 numbers? So remember here, you get a value, but you're going to consider the negative and the positive of that number. So it'll be negative, whatever number you get, and that'll be for that first box here. And then the positive value of that here. Now you're going to ask yourself, if you were to have this on a number line, negative, so when you multiply that again using a calculator, and the positive is over here, right? The positive number. Does 1.74, is it between them? Meaning it's within, or is it outside of it? So is it somewhere, well, 1.74 might be in the positive area, but if it is in this area, so if it's between those 2 numbers, it is going to be considered, this green area is within. If it is outside, right? It's going to be considered the word outside. So if it's green, if the number line, right, 1.74 is inside between those 2 numbers, it's considered within, or is it considered outside? So you'll go ahead and select that there. So moving into part B. So because if it does fall inside, it's, remember the idea is that we're looking for that 5%. So we're looking at if it's actually on the outside part. If it's inside, it's considered not statistically significant. If it is inside, it is considered statistically significant. So you should have gotten that it is outside. So So because it's outside, you're going to ignore the first two options here. Because it falls outside, it is considered statistically significant. But because it falls outside of the 5% or it falls in within the 5% significance level. So the key word you have to watch out for is that now they're talking about significance level. So because it is outside of the interval, that means it falls within the 5% significance level. I know we're using a lot of the same words again, and it's just a little bit of like how it overlaps, and it can be a little bit confusing because in the previous we said that it falls outside of the confidence interval, but because it's outside, it means that it is statistically significant. And in other words, from the previous task when we were doing the research about the fertilizer and wearing the watch, because it's statistically significant, it falls within the 5% or it's less than that 5% significance level. And now that we know it is statistically significant, right? What does that mean in terms of buying the red box versus the blue box, right? So right there in your statement for part C, we are going to go ahead and mention it because it is statistically significant. There are people that would technically choose a pasta box because based off of the color of the boxes in. I think even personally for me, I think all my pasta boxes are in blue. So and that's just coming on from like learning from family how to cook, right? The idea is I most likely will buy the same type of brand, which is in a blue box. I don't think I've ever bought something in a different color. I know there's packaging in red, but there is some type of science back to it on what color we choose and what we want to see. Because the blue box was actually higher in terms of the mean, it does show also that there is a preference that people will choose the blue box over the red box. So kind of the ideas that I described there, you're going to go ahead and put that there for part C. So again, make sure you're including that because it's statistically significant, there's a difference when people choose the red box over the blue box. And you're done with this activity, and go ahead and make sure you submit that for score.